Okay. Maraming salamat sa lahat ng dumalo. Thank you, sis, for that introduction. So now I will share my slides no, to show to you the results and output of Project eSmart after 1 year of implementation. Can you see my slides? Okay. Um, okay. The where, the how, and the when of Manila-based hydrodynamics. So for any rehabilitation effort or management of any water body, it's important for us to answer the question where. So where is the source of the problem? Or where do we start in rehabilitation of that specific area? Or maybe we want to answer how. How can we arrive at a solution? How do these problems originate? Or maybe we want to answer when. When is the right time for us to have rehabilitate? Or maybe when do we target the cleaning efforts so that the efforts will all become effective. And so here I present to you the initial findings and assessment for Project eSmart. Okay, to go through the presentation outline, I will quickly go through the objectives and methodologies of the project and then go straight to the output, meaning what have been discovered or what are the results based on the studies done by the project. And then come up with scenario analysis for us to better appreciate the results of Project eSmart. So for any solution intervention that we want to implement in a water resource system, such as that of the Manila Bay, we always need to look at the bigger picture. Okay, we cannot just target Manila Bay as is. No? So we need to determine what water bodies interact with the bay, what linked ecosystems are also contributing to the state or status of Manila Bay. And for us to be able to do that, we need to determine how these systems are interrelated. The watersheds, the linked ecosystems such as that of the Pasig River and Laguna Lake, and that of the entire watershed. Okay. And so for us to be able to come up para maka-arrive po tayo sa better understanding ng ating target area which is Manila Bay for this case, we need to make use of models or numerical models for understanding the system better. So the key to any rehabilitation effort is really understanding the system so that we know how to target, when to target, and what to target in the solution uh, interventions. And so the primary objective of this project is to streamline solution interventions with the use of numerical modeling analysis of the integrated Manila Bay, Pasig River, and the Laguna Lake and surrounding watershed system. And considering the pandemic and the limitation for data gathering or primary data gathering, we are very much appreciative of the contribution of the different agencies in sharing to us the secondary data that form the baseline information for us to generate the models that we are using now. Specifically, the digital elevation models, the land covers, and then the rainfall data, discharge data, and different hydrometeor information that came from different government agencies and linked institutions. So maraming salamat po for that. No? Because of that, we were able to set up our models well represented by the physics of the study area. Okay, and so we were able to come up with and set up our hydrologic model. So hydrologic model po, this is that representation of how much water is transported from the watershed ng ating study area, which is Manila Bay. And for us to be able to consider the entire area, this large area here of the watershed, we need to use models for us to quantify how much is discharged into Manila Bay, for example. And for us to be able to do that, we set up models describing this entire large watershed, which is roughly around 17,000 square kilometers of area. Okay, So utilizing digital elevation information, land covers, soil representing the area, and then rainfall information on historical and short term, and then with discharge information, for example, you're able to calibrate and validate the models and come up with representative discharges from the entire watershed of Manila Bay. Okay? And for us to be able to make sure that our models are robust and are able to replicate on the actual conditions of the hydrology of the Manila Bay watershed na we needed to calibrate. No? So calibrate po ang proseso where we adjust hydrologic parameters so that the models will be able to replicate yung actual discharge data or information. And we did that for several basins depending on the available or the availability of the discharge information. Okay? And so, based on the hydrologic modeling, we were able to quantify historical values of river discharges. These are continuous daily discharges since the 1970s until the present time. Now we have river discharge information for all the rivers that are discharging to the integrated Manila Bay, Pasig River, and Laguna Lake system. So you can see here that among the basins that contribute the most in freshwater input to Manila Bay, Pampanga is the largest at around 5,260 cubic meters per second, and that's a total annual. And then followed by the Laguna Divide Basin of around 1,250 cubic meters. So those two large watersheds contribute the most to the freshwater influx of Manila Bay. And then correspondingly, we move on now to the hydrodynamic model. So this is the part where we model the open water conditions of the integrated Manila Bay, Pasig River, and Laguna Lake. Something like this one. So we want to know how water moves within this integrated system. And for us to be able to capture such dynamic exchange of waters between these two large bodies, we needed to set up a model that is integrated, as you can see in this figure. And correspondingly, we inputted all the hydrologic output of these river discharges around Manila Bay together with that of Laguna de Bay. And so we were able to come up with a hydrodynamic model that is representative of the actual conditions as that can be observed on the field. So something like this, we calibrate in terms of water level for now, at least for Manila, Laguna de Bay. In this one, so you can also see the comparison with the tidal conditions of Manila Bay, where we were able to come up with relatively good models already. So that we can say that later, if you want to utilize these models for scenario analysis, we can say that we can now foresee how the integrated Manila Bay, Pasig River, and Laguna Lake system would respond to different management interventions. Okay, so this one basically shows you the dry season conditions simulated between May 20 to June 3 between the near surface and the near bottom conditions. I will now focus more on the discussion on the dynamics of Manila Bay. So you can see here that during this time, much of the water movement is counterclockwise because of the prevailing wind, which is southeast during this period, at least for the near surface. For the near bottom, it's really more of because of the tidal signal, in and out, depending on the high tide and the low tide or the flooding and the ebbing conditions. And then moving forward, these are just snapshots for different tide conditions. So I will describe here. Spring tide is the time when the difference between the range of the low tide and the high tide are highest within the month. And flood tide is the condition, tidal condition from low tide going to high tide. So much of the waters can be expected to flow in to the bay, as you can see here, the near bottom and the near surface current conditions are flowing into the bay. And because this is during a flood tide condition, and it happens no, during a spring tide condition. And then for the ebb tide condition, on the other hand, ebbing is the condition from high tide going to low tide. So much of the tidal waters are moving out of the bay. As you can see here, for the near surface and the near bottom, there's a difference in flow dynamics, which is very representative no, of the estuarine flow condition. Pag sinabi po natin estuarine flow condition, there's a separation no, between the near surface and the near bottom no, flow dynamics. As you can see here, the near bottom is sluggish, no, but moving inside the bay, but the near surface no, is ebbing and moving out of the bay with a counterclockwise flow direction. Okay, and then we move on to the neap tide conditions during the dry season. So neap tide po, this one is the lowest tidal range within the month. Okay, so you can, or within the tidal cycle. So you can see here that during the flood tide, no, near surface waters are moving upstream, okay, but at a much lower no, current velocity as compared during the spring tide conditions, and the near bottom no, is also moving inside. Then during the ebb tide conditions, so moving out naman, no, out of the bay, okay, and then the near bottom is still moving in, but at a more sluggish or slow velocity distribution. So as we can see here, no, paiba-iba po, no, on how the current or the water is moving within the bay, depending on the timing no, within the month, okay, and the prevailing wind conditions. And it just emphasizes no, that Manila Bay hydrodynamics is mainly defined by number one, river discharges coming from its watershed. Number two, the tides that are coming from offshore. And number three, the wind conditions that are pressing no, or stressing on the surface of the water body. Okay, and then these are the conditions naman no, pagdating po ng wet season. No? So, mas intense po to no, because we can expect that there is more fresh water coming from the watershed of the bay. And so, the difference between the fresh water and the salt water no, will tend to induce yung tinatawag po natin density-induced currents. Okay, as we can see from this animation, you can see again, no, there's a difference between the near surface and the near bottom conditions. So moving forward again with the snapshots, the spring tide condition, flood tide, during this time when the wet season arrives, no, the prevailing wind is more southwest. And so we can expect that the wind is affecting no, yung flow condition. So kanina, it's counterclockwise. Now we can expect a clockwise no, gyre circulation of the near surface current during the wet season. The near bottom is coming in as the salt water flux no, is much heavier and is coming into the bay during a flood tide condition. Moving forward, no, during ebb tide, no, ito po yung time where much of the waters are flushed out with the aid of the river discharges. No, these are more intense now. No, moving out tide and the fresh water flows no, are moving out of the bay. So you can see that the fresh water po that is coming from the watershed is mainly near the surface. Samantalang near the bottom, it's mainly incoming flows no, from the offshore salt water or seawater. Okay, these are conditions during mid tide. So these are during the times when the tidal range are shortest. We can expect no, much lower no, flow velocities, but the gyre circulation, which is clockwise, is maintained again near the surface because of the prevailing southwest monsoon condition. And then the near bottom is flushing in no, from towards the bayhead. No, offshore water is coming in at the near bottom conditions. And then this is the condition during mid tide. Again, the ebb tide conditions, no, palabas ng tubig. And so the gyre is still there, but much more weaker, and then sluggish bottom conditions. Okay, so if we try to remove now no, the effect of tides, no, which is mainly tries to affect no, yung water movement because of yung labas-masok ng tubig no, coming from offshore, a good way to see this is using residual current analysis. So this is the part where we remove tide or we average the tide conditions and see how wind and river discharge flux affect the circulation patterns. So these are the conditions during the dry season. As you can see here, the wind conditions are from the southeast, and then the gas circulation remains to be counterclockwise with this general flow circulation. And then the bottom currents are moving in towards the bay. So these are more important for assessing yung tinatawag nating material transport. Yung, if we want to know or we want to learn how any particle or material will be transported or gumalaw within the bay, kailangan po natin tignan yung tinatawag nating residual current. Ito po yung mas long-term yung effect because the tides are just coming in, going out, and it repeats within the day, within a month, and so on. But this one uh, is much more for the long term. Okay, and then these are the conditions during the wet season. So you can see the gas circulation is now clockwise, again because of the southwest monsoon, but the bottom current remains to be towards the bay head. Also, because of the integrated model that we have set up, na-capture po natin yung pasok labas ng salt water into Manila, to Laguna de Bay, which is a good validation of the water quality feature of our model, which shows that it satisfies yung observed, where in 2018 there is salinity intrusion that happened. Take note that salinity intrusion is not a yearly thing for Laguna Lake. It depends on the hydrology of Laguna de Bay. So if Laguna Lake has little rainfall during the year, so we can expect much salt water to flush in or to intrude. But if it has enough precipitation within the year, and then lake levels are high enough not to let or intrude, let the salt water from Manila Bay to intrude. So our model was also able to capture this dynamic condition or interaction between Laguna de Bay and Manila Bay. And so now with the models that we have, we can go on explore different environmental scenarios. Yung mga tinatawag po natin what if or what ifs condition. Because we have a model, if you want to explore any management intervention or maybe any conservation scenario, we now can make use of these models and see how the system will first respond before we do any actual action in the field or bago tayo gumastos for this intervention. And then we get to have a better understanding of the hydrodynamics of the integrated system. So for example, if you want to see, for example, yung changing land covers impact on the hydrology of Manila Bay watershed. So we have observed, based on the data that we were able to gather from Manila, that through the years, since 1988 until the present, we have changing land covers within the watershed of Manila Bay, as specified in detail by these ones. So, kitang-kita lang dito is yung red one, urban area has increased from 1988 until 2015. So others also increased vegetation and so on. So it depends on the location. Some urban areas extended or expanded. Some rural areas even became more vegetated. Okay, so with these changes in land cover conditions, will there be an effect or impact on the hydrology or expected discharges from these basins? As can be seen by the result of our analysis, it depends on the location. So some areas have increased discharges. So ang assumption po dito is if we use the same land cover for the same rainfall event within a year, how will the changes in river discharges become? So depending on the watershed, you have portions which increase, some decrease. So what is observable here is that for the Laguna de Bay Basin, for example, which is much more urban as compared to the other watersheds, it has a significant increase in surface runoff. So now much of the water is being transported on the surface of the landscapes rather than or before even going downwards towards the groundwater. So this can be seen further or in more detail here, where depending on the basin, A comparison between the 1988 and 2015 condition shows that for Pampanga River Basin, there's a decrease in surface runoff, but for Laguna de Bay Basin, there is a corresponding increase. Again, that has something to do with the landscape. No? And this is quite important to present, mainly because if you want to manage even those areas far within the watershed of Manila Bay has a corresponding impact to the Manila Bay environment. Mainly because it will affect the corresponding hydrology and the discharges that can be expected to drain towards Manila Bay. So even if we are as far as in Pampanga, so we will have an effect or impact on the management of Manila Bay. So moving forward, just to emphasize on the impact of the discharges to Manila Bay, and what if mag-emulate tayo, what if walang river discharges to Manila Bay? How will it show na there is a difference in the circulation patterns within the bay? As we can see in the residual current analysis during the dry season, this is the condition if we have the regular discharges toward river discharges toward Manila Bay, and this is the case where we don't have any freshwater discharge. So there's a significant effect, even if you have your winds here, okay? So you can see that for a wind discharge, you can see the large circulation to be present, as we had seen earlier. But if we don't have the freshwater discharge, or if the freshwater discharge are changed, you can expect such a change in the flow conditions of the bay. So we can see how important the river discharges are in the simulation of the hydrodynamics of Manila Bay. So you can see the conditions here. Okay, dry season conditions, similarly, will have corresponding differences. The wet season conditions, near surface, okay, so a significant difference between the two conditions. And then this one, near bottom, you can see how much is the change in circulation pattern near the bottom between a with freshwater discharge in Manila Bay and without a freshwater discharge. Okay, and then laruin pa natin yung model. What if we have an oil spill scenario in Pasig River? So sabihin natin sa may Santa Ana Ferry Station. And so we can play around the model. Since it's now robust and it's representing the system, let's see how different will the oil slick move or distribute within the bay if the slick is or the oil spill happens at different times of the year. So this is the condition during the dry season. As you can see here, much of the slick are distributed both at the north western shore and at the southeastern shore, distributed all over the bay. But during the wet season, much of the slick is concentrated on the Cavite shoreline. So it did not even reach the Pampanga Bay. So for any cleanup operation, may it be oil slick or oil spill or probably any pollutant. Depending on the time, we can actually target where to focus first for an effective cleanup operation. Okay, these are just snapshots just to emphasize on the difference in the distribution of the oil spill depending on the time of release of the spill. So 10 days, 40 days, and 80 days condition. So what if we have now a pollutant, and then we get to instead model oil, we model a particle that is representative of a pollutant. And so this one shows you a 1 year Pasig River pollutant release towards Manila Bay. So as you can see here, it almost takes like around 9 months before all the materials are removed out of the bay, which is almost gives us an idea of the hydraulic residence time of the bay. So to look further, during the 1 year release, these are the conditions at 0.5, 1.5 months, and so on and so forth, roughly around 10 months. And then this is the difference between two different releases, one in the dry season and one in the wet season. So similar to the oil slick, or the oil slick is much lower, but this one, much of the concentration concentrate were found, no, in Pampanga Bay during the dry season, while during the wet season they are much more concentrated along Bacoor Bay and along Cavite shoreline. These are just snapshots describing the difference between the dry season and the wet season. And then we can again, no, simulate something like what are the expected impacts of the planned coastal developments in Manila Bay. Of course, no, modeling will have their limitation, but at least with such a representation, no, we can already have an idea of the possible impacts of such coastal developments. So another what if here is that there are a lot of reclamation projects, no, that have been um, proposed, no, and some are already accepted. Okay, and so what if all of these proposed, no, later on will be there in Manila Bay? What will it have an effect on the circulation patterns of Manila Bay? So we can do a with and without scenario. So this one now shows you, the simulation between a with reclamation and a without reclamation scenario, where we can already see, that the waters here, are stagnated because of the presence of the reclamation area. And so at the confluence, at the restricted the channels formed, because of these large developments, we can expect changes in the water movement. Okay, so these are just snapshots, comparing the without and the with reclamation scenario. I think we can look into more detail here, where specific locations, there's a significant increase in current. Okay, so take note, these currents are depth average current. So we can see that there's an increase now when there is already, an obstruction, because of the reclamation. So take note that these are normal conditions. We can expect that these velocities will even become faster, if there is a storm event or a typhoon condition. So this only shows us different locations, the width uh, reclamation, the blue line, here shows faster moving current as compared to the red line, which shows, a slower moving current, for a with and without reclamation scenario. Okay, so you can see here further, in Cavite during the wet season, there is a weaker velocity because again of the effect of the presence of the reclamation areas here, added into the model. Okay. And lastly, we were also able to come up, with a hydraulic model, of the coastal area in Bulacan. So this is a flooding condition analysis during, you all know this, na September 26, this is Typhoon Ondoy. So this is just an animation of the maximum flood depth, that is expected in the Bulacan River Basin, which is in coastal Manila Bay also. You know that there is an ongoing large coastal development in that area. So if we just, this is the case where there are no obstructions, near the coastline or no developments. So this is how the flood envelopes in the river basin, for a no development condition. So this one shows us if there is a large development in this area, for example, so we can expect the difference in flood depth for a with and without flood condition, which says that this yellow or light green area here, is an increase in flood depth because of an expected development in this locality, which is around half meter depth of flood depth. So that is on the condition that, of course, no flood control or no drainage systems that are effective enough will be placed to um, remove the possible effect, of these added flooding conditions. And so I summarize, my our 1 year of project output, where we were finally able to come up with a robust hydrodynamic model for year one, because we are projecting at a water quality model for year two that is able to describe the basic characteristics of the system within acceptable accuracy. So it was also shown that the Manila Bay hydrodynamics is governed by tides, freshwater discharges, and atmospheric forcing due to wind. Okay, and there is significant exchange with the outer sea, the West Philippine Sea. So this corresponds to important implications to the hydraulic residence characteristics and material transport features of Manila Bay. And so with the calibrated and validated model that we have now, scenario analysis can now be performed for supporting resource use and conservation management decision making. So we can play around with the model and have a better feel of how Manila Bay responds to different forcing mechanisms. So may it be something good or may it be something bad. So better understanding would mean better management of the Manila Bay environment. Okay, I think that ends my presentation. Thank you.